Rahul Anil Kulkarni is from Intel as well, where he is SOC lead design engineer. The title of his talk is Strategies Devised to Shift Left Verification of Chiplet Disaggregation Design. And in terms of bio, Rahul is a disaggregation design architecture in Intel Graphics Division, held a master's degree in VLSI and 19 years of semiconductor industry experience with different roles of architect, microarchitect, design verification in various domains such as processor ALU, accelerators, routers, and disaggregation. And he's got the next 10 minutes. Over to you. Thank you, Rahul.
Hey, thanks, Mike, for that generous introduction. Good morning and good evening, everyone. So thanks for the opportunity to speak today on this topic. I'm gonna talk about the strategies that we deployed to shift left verification of a chiplet disaggregation design. Okay. So let's understand what is a chiplet disaggregation design, right? So as you can see in the diagram, in a SOP system, there could be two or more multiple chiplets, right? With different IPs, which could be GPU, CPU, or even for that matter, a split GPU, right? Those would be talking with each other through the bumps. As I have shown, there are bumps that you can see on the chiplets, and the bumps are connected with the base chiplet to get the routes done, right? So naturally, disaggregation design is the microarchitecture that supports the different logical protocols to transfer from one chiplet to other through the physical medium. Okay. Essentially, it has two components, two mating components, I would say, which is transmit logic TX block on one die that talks with the receiver logic on the other die. So as you can see, this would be a pretty tuned block, right? And there is a lot of interaction between them. Okay. Traditionally, and the protocols that generally transfer between the chiplets are generally bidirectional, right? And such logic, as a typical high-speed design, uses clock forwarding architectures, right? That is a very predominant architecture that is used. We have seen that these chiplets are bonded with different technology bumps, right? And gradually the bump sizes and bump pitches are reducing, helping us to, densely pack these chiplets, right? Point to note is each chiplet is a self-sufficient, and then again, each chiplet can be on a different manufacturing process, right? So this is a typical design. Now let's look at the verification challenges of such a system, right? So we already seen that design is highly interdependent on the TX and RX blocks, right? And when such blocks are split across the chiplet, often these chiplets are either externally sourced or there are different development teams involved in large companies, right? And each such team has their own timeline, their own design code, integration processes, right? And even the manufacturing processes and heaps and chips could be differently developed, right? So while ideally the best case would be a SOP level integration that need to happen so that we can verify the whole system, but such SOP level model buildings are often a long drawn process, and it often starts late for rightful reasons, right? Because it's different development environments. It's again a resource heavy task to simulate at such a bigger level, right? So point being, naturally, even for a basic verification checkout or feedback of this TX and RX module, we have to wait for the SOP level integration, which is not what anyone would want. We would want a chiplet to be a standalone verifiable, right? But again, chiplet, if you see, its boundaries are basically the micro bumps. It is not exactly the logical protocol. There would be a lot of bundling and physical aspect, right? So verifying at chiplet boundaries at microbump is a challenging task. So what we have done, basically strategy-wise, is so to verify functionality first. Let me show you one example, right? So what we have done is build a test bench environment with the complementary TX and RX functions, right, which would act as a BFM. Now, this need not be exactly full-fledged TX and RX code-wise because they need to act as BFM. But point being, they are readily available, easier to integrate because they are developed on the same chiplet. And now what that enables us is use protocol level BFMs at the entry and exit, right? So I don't have to worry anymore about the microbump interface. I can just keep on using the protocol BFMs and the other infrastructure like typical testing queues and data integrity, data order checks, which would naturally be present if the design was not disaggregated, right? For a monolithic design, such things, protocol level handling and checking is already present. Now I am enabling the same infrastructure even to check the disaggregation boundaries. Okay, so this gives a lot of reuse, and actually it helps lower NRE cost, right? And as the protocol evolves, naturally these BFMs and structures evolves naturally. So whether we choose a monolithic approach for particular program or disaggregated approach for particular program, I do have continuity of the verification environment. So this actually helped shift left some of the functional checkout, right? And my last slide here is on the repair. So functionality we checked. Repair is something that comes as an artifact of being disaggregated, right? So some of the micro bumps during manufacturing, they can get misaligned or mispackaged or could be burnt out, right? So you see the micro bump to micro bump connection may not be as intended. Now what repair allows is, it's a feature that allows a redundancy. So we need not use this bit or this link, but actually shift the data on TX side and again unship the data on RX side. Okay. Now to validate this, what we had done is basically we injected a garbage data here or like a X inject, and then ran the existing checker at protocol level. So if there is a issue with design that it's not correctly shifting in and shifting out, it would be caught at end-to-end level. So this gives us good negative testing that things are working fine even with the fault in microbump. To test repair positively that indeed a microbump, this faulted microbump data is shifted onto this bump, right? We also developed a system Verilog based BFM to mimic
last minute,
the
please,
functionality.
Rahul, you should be wrapping up now, please.
Okay. Am I audible, Mike?
Yeah, last minute. I just said last minute now.
Yeah. Okay, sure. Yeah. So this is how we tested the repair functionality. So these were the strategies that we applied in the some of the graphics product where we did the disaggregations inside graphics IP. Thank you. That's it I have.
Again, perfect timing. Thank you. So thank you very much, Rahul.